I should be here. Can you hear me?
Can hear you, Steve.
Okay, good.
Matthew, you can hear Steve fine.
Yes.
Good, Matt.
Hi, can I please ask all panelists to mute at this point? Good evening, members. I'm just giving it a minute or two for more attendees to join, and then we'll begin formally. Good evening to our members from Durban and our guests nationally and internationally. SAICE Durban welcomes you to 2022 and many compliments of the season. Although it's a month in, and I know we have moved on from the silly season, here in Durban, we are definitely in the roasting season as the temperatures here in Durban are soaring like the fuel price in South Africa. Okay, so it gives me immense pleasure to present the AGM for our Durban branch for 2022. I am the current chair of the branch, and if you haven't met me before, I am Sharon Shanmugam. At this stage, I'd like to bring the agenda up on the screen. And whilst this is an agenda that is more for the traditional AGM and it's for in-person events, I'd like you guys to please use the reaction buttons such as the thumbs up or the like button in order to confirm or propose. So please, at this point, can I get a confirmation for the agenda and then a seconder? Thank you. I see these up on the screen. Kavita, can I just ask you to take down the names of the confirmer and the seconder? Okay. Do we have any proxy votes that are for our committee members in Durban? If so, can you please put it up on the chat box now? I will give you a second to do, a minute to do so. Okay, thank you. I do not see any confirmation of proxy votes, so I'm assuming we can go ahead. I can confirm that there's a quorum at the meeting for this evening. And then I'd like for somebody to please confirm the minutes for 2021's AGM. You would have received it by email in the last 2 weeks from Kavita. Thank you. I see a confirmation. Please, can I get a seconder? Can somebody please second? Thank you. Cav, please just make a note of those. Okay, so at this point, I'm going to quickly go through my chairperson's report for 2021. Okay, in 2021, we were very lucky to move away from the pandemic and get into more in-person events. But I'd like to highlight what I believe are the 10 top events that we held in the previous year. We held towards the end of the year a very incredible and the event that I thought moved us into a new space as a committee, and this was the webinars that we held over 10 weeks in conjunction with UKZN and Sanlam. During these events, we managed to cover a broad range of topics through many leaders in the industry, and we were able to secure 1 CPD point for attendance at all 10 events. In parallel to that, we held our virtual site visit with the team from SMEC South Africa to the Mzikaba River Bridge to cover what is going on down the road from us in that unbelievable project. And then in August of 2021, we held our first sold out in-person event to 50 women who attended a luncheon in the Bond Shed in central Durban. And this was an incredible event where our keynote speakers were the CEO of SMEC South Africa, Logeshri Sunarayan, and the president of 2021, Mr. Vishal Krishnadath. Then we held our online speed mentoring in conjunction with KTech, and at this event, we were able to provide mentoring for DUT, MUT, and UKZN students. We held our winter warmth outreach program, which has been running for a few years now, but last year was especially special considering that we were in the middle of the pandemic and our industry was going through quite a bit as well. At the end of it, with the support of many corporates, we were able to provide blankets for 400 kids from 4 institutions in the Greater Durban area. We also reintroduced our 30th bridge building competition, which was held as a hybrid alongside BMK. And we were able to have winners that were sent up to the national office who participated in the national competition. Our LIC and LIC5 and LIC7 training was one of our successful events for the year, where we were able to train at least 18 students per month. We hold this training alongside Naidu Consulting, and we look forward to increasing our reach and our ability to keep our members up to date with LIC over the course of 2022. In 2021, we made a market attempt to reignite our social media platforms. And if I may say so myself, I believe our platforms were just lit. We did the Celebrate a Civil Engineer, and we did the Choose to Challenge series. During these 2 series, we profiled a number of leaders in our industry. And whilst it started off as just an event that, or just a platform where we could give people the chance to see the amazing talent we have in the industry, it turned out to be a national event where people all across the country started to reconnect, having not spoken for years, be it due to distance or the pandemic. But this platform allowed people to reconnect both socially and business-wise. Then we finished off the year with quite a bang, and I'm not even sure if everyone's recovered from this, but we had our SAICE Durban Golf Day at the Mount Edgecombe Golf Club around the mid of November, and we had a sold-out event with 120 golfers, all enjoying an amazing day with incredible prizes, and I'm definitely looking forward to our 2022 Golf Day. We also took the stance to reignite our Outlook magazine. I have it on good authority that our latest Outlook went out just the other day. So I hope you guys are enjoying our new Outlook, which is a thicker, more glossier version. And yeah, it has more content. So hopefully you guys are enjoying that. Okay, at this point, I am going to now call upon my treasurer for 2021, who was or who is my friend and my colleague, Mrs. Teresa Mjenge, and she will present the treasurer's report for 2021 to you.
Thank you, Madam Chair. Next slide, please. I will just take you through the balance sheet. It's a lot of numbers, and maybe to the members who are on the webinar, if you require a copy of the report, you can contact our admin if you need to go through the numbers in detail. However, I just would like to highlight that in terms of our current assets, we had a marked increase of over 100,000. Next page. Next slide. In terms of our income to date, you will notice that we had a significant increase in income, and this was attributed to LIC training, as has been already alluded by our branch chair. The training was mainly done online, and we had an increase of over 150% growth in LIC income, which increase was about 487,000. So I would like to just thank all the members and the companies who assisted their employees to enroll for these courses. Next slide, please. Our expenditure, we tried as much as possible to minimize expenditure, and we mainly focused on the reduction of debt. There was debt, which was bad debt, which was dating back as far as 2017. And with our new administrator, there were main inroads in terms of communication with debts. We managed to recover almost 80% of the debt without the involvement of debt collectors. If you notice from the numbers, you will see that our bad debt is significantly reduced. Next slide, please. This is my most favorite slide because for this year, 2021, we had an incredible surplus of 333,000, coming back from a deficit of 700,000 odd. So I would really like to thank all the members and the corporate for the support. Next slide, please. In summary, I would like to advise all the members on board that our finances are healthy. And although we started off in a deficit, we managed to turn around the situation to create a surplus. There was a significant reduction of debt from 300,000 to 47,000. And this I would like to personally attribute to our administrator who has excellent communication skills and be able to persuade our debtors to pay off. There was also aggressive marketing for online courses, and most of our online courses, especially labor intensive training 5 and 7, they were sold out, and we really need to pat ourselves on the back for being able to achieve that in such a very difficult environment of COVID, with many firms either scaling down or even retrenching. On a sad note, I would like to request the AGM to give us authority to write off the outstanding bad debt of 47,000, because I believe that the time or cost that we would incur to recover this debt, since we've already failed to further recover it in the past financial year, would not be value for money. So I request that we resolve to write it off. We have an investment account at Investec. We have earned interest of 8,000 for the year 2021. And I am happy also to announce that although we started off on a deficit, there was never any one point where we had to take out money from our investment account. So I want to believe we have run our finances well, and the corporate and members have supported the initiatives through attendance to events and also through attendance to training. And I thank you very much for the support. Thank you very much, Madam Chair.
Thank you very much, Teresa, for that wonderful news. And yes, it's only thanks to our members and to the corporates here that have supported us over the year that we were able to make this change. So at this point, can I just please again get a summary to motion and adopt the treasurer's report? And if there's any issues with adopting the resolution to write off the debt, can I ask that you just put it into the chat box? And if there is, we will address this via email with yourself and Kavita and the committee going forward. So I'm going to give you a minute and just put something into the chat box if you have any issues, and if not, then we're going to proceed. Okay, perfect. So on to the next part of our AGM. Let us go into the election of the committee for 2022. Okay, so I'm going to put up a slide with the committee nominations. The nominations for the committee in 2022 were gained from the nomination form that we sent out via email to the members in Durban. And the nominations are myself, Nathan Munsami, Shivam Suknandan, Teresa Mjenge, Kyle Chetty, Yoshni Patel, Maxine Jacob, Professor Phil Everett, Ayanda Mpanza, Sishle Mshlongo, Sam Pule, Alan Clark, Mawan Dumusa, Kwadla, Natanya Padyachi, Smriti Singh, Vuyo Dlamini, and for an MUT rep. Okay, I'd like you to just also give a moment's acknowledgement to those members that, or those committee members rather, that have resigned from the previous year, and that's Blaise Jacob, Kamira Naidu, Tabiso Dladla, Samantha Naidu, and Josh Padyachi. I'm also recently told that Teresa is resigning from her position as treasurer, but she'll remain as part of the committee. I just want to thank each and every one of them for their contributions to the committee, and I wish them well, and I hope that we can work with them behind the scenes and still continue to gain from the value that they've been able to give us in the past as well. Okay, so can you just take a moment now to reflect on the names? If you feel that there should be any more nominations, then please put them into the chat box. I will give you a minute to do this. Okay, I don't see any reactions. So I take it that everybody in our Durban committee or Durban branch rather is happy to adopt the committee for 2022. Okay, so with that, it gives me great pleasure to introduce the SAICE Durban Committee for 2022 on the basis that the members would warrant the team as I have proposed. We held a strategy session last week and we voted internally for roles within the committee. With this, may I introduce the committee with their roles. I am grateful to have been voted in as chair again for 2022. My vice chair is Shivam Sukhnandan, and the treasurer going forward is going to be Kyle Chetty. We have Nathan Munsami, who will remain in his position as vice chair, and we have Maxine Jacob, who is taking the position of vice chair-elect. Our remaining committee members will be some familiar faces and some new ones. Let's begin with the familiar faces, starting off with Yoshni Patel, and then Teresa Mjenge, who you've heard from just now, Ayanda Mpanza from SAICE, Sishle Mshlongo from the eThekwini municipality. And then we have some new faces who are Alan Clark from HALC Africa and Natanya Pujachi from Macaferi, and then Mawan Dumusa, who is in between jobs right now. Then we have a familiar face from previous years who's rejoining us. Welcome back, Sam Pillay. And then we have our most famous committee member, Professor Phil Everett, who will remain as a co-opt this year. Kavita remains as the branch manager or branch coordinator for the year. And then our student chapter reps will be Smriti Singh, who will represent UKZN, and Vuyo Dlamini, who will represent DUT. And then we have to still confirm our MUT representative, but I will keep you informed of that as we head into the next branch meeting. At this point, I am going to cover my address as the chairperson for 2022, and I'm going to try and keep it as short as possible. The first order of business that I have is I'm going to introduce our logo and our theme for the year. Our logo and our theme for the year will be up on your screen right now. And our theme for the year is our opportunity to engineer the tomorrow we desire for our country, our community, and our industry. It's building on the previous year's themes where I wanted to become more focused on creating opportunity for the corners of society that we serve and that rely upon us. These being the country, our community, and our industry. All of our initiatives for the year will be designed to ensure upliftment in each of these societal spheres. We have arranged our calendars to bring more in-person events and ensure that all of these will be CPD accredited. We will aim to hold 3 branch meetings in the year in person, whilst the remainder will be virtual. There will be events that will be focused on special days of acknowledgement, such as World Engineering Day, Water Week, Transportation Month, and the like. Teresa, Yoshni, and Sishle will be spearheading 2 community outreach programs this year. One will be centered around the scholars, and the other will be centered around the underprivileged. Many of the activities that we've seen in previous years, such as bridge building, equilibrium, and speed mentoring, will remain on the calendar. I would like to draw your attention that the main event that was not held in the previous 2 years, and this was the SAICE Durbin Awards. Whilst in 2021, SAICE Durban was still the largest contributor by far to the awards for the national office, we were not able to hold our flagship event for the year because the number of awards we attracted was just not enough to warrant our own event. So this year, we are hoping to kick off a campaign very early in the year in order to host our own awards. And I hope that I can have the support of our local industry in order to bring this back to onto the calendar. LIC and LIC 5 and LIC 7 will remain irregular on the training calendar, and we are looking at introducing a 2-day LIC training alongside Naidu Consulting. So please continue to support this. Mr. Tom McEwen will be running the geometrics course as he has in the past. The first one is being run on the 21st to the 25th of February. Kavita will put up some details on the chat box detailing the specifics around the event for the 21st to the 25th. And I hope that you guys can support or ask your companies to send the relevant people on these courses. I urge you to please follow us on social media, where we will continue our tradition of engagement and profiling of important people and events in our industry. I'm proud to announce that our Women's Day luncheon is already well supported, as our keynote speaker has already been confirmed, and she is none other than President of SAICE 2022, who is Professor Marianne van der Skeren. And so we are already looking forward to an incredible Women's Day event. Having spoken to the guys at the strategy session last week, I am very proud to announce that our SAICE Durban Golf Day for 2022 already has taken. So I'm ensured that we will be ending this year with a bang. And hopefully with all of this, we can keep the branch of the year title in Durban and make it one for 2022 as well. With this, I come to the end of my SAICE Chairperson address. If there are any questions, you guys are more than welcome to address them via the chat box or via email with Kavita, and I will be able to respond to any questions. Before I head into the main event for the evening, I'd like to take a moment for you to notice the names on the screen. And these are our long-serving members, stalwarts in the industry, greatest contributors, and they have been on the SAICE committee they have been SAICE members and part of committees for more than 4 decades. I'd like to thank them for their long service to SAICE and to the industry, and I wish them well. Okay, thank you very much. With that, I'd like to ask anyone who has general comments to put them into the chat box. I can address them at the end of the event or via email, as I just stated. At this point, I'm going to switch my camera off and hand you over to our sponsor for the evening, who will be represented by Mr. Alex Axelrod, who is the Group Technical Manager for Moulders, and he will introduce our keynote speaker. Welcome, Eric.
Thank you. Thanks for that intro. I'm certainly not the sponsor myself. That's my boss. Good evening, everyone. I'm Eric Axelrod. I'm a humble chemical engineer, and I live to serve as the group technical manager for a company called Moulders. And I've just realized that I haven't started sharing my screen. So hopefully we can see that now. Maybe, there we go. So Moulders, who have partnered with SAICE to host this event today. We are probably the biggest EPS, that's expanded polystyrene, converter in Southern Africa, and we are part of Saudi Holdings, which is a group of companies. You might recognize a couple of them there. Dormac are the shipbuilding, ship repairs company. Concord Refrigeration, Park Homes, which do the modular classrooms and site offices, Rudnev Refrigeration, Gascon, Southpan, among a few in the group. Geographically, AGM Moulders has a national footprint. We have 5 factories throughout South Africa and all the major centers. We have Atlantis and Cape Town, Boysons in the Johannesburg area, and then in Durban, where I sit, that's our head office. We're in Jacobs. Ezekiel, which is Ladysmith, and then on the north coast we have Isitebi factories. When it comes to Geofoam, we produce to an American standard, ASTM 6817, and we can supply densities of material from 12 kilograms per cube all the way up to 40 kilograms per cubic meter. So when you think about it, that's extremely light. That's a cubic meter of material that only weighs somewhere between 12 and 40 kilograms, which you can easily lift by yourself, which is phenomenal, and it has an impressive strength characteristics, or compressive strength characteristics also, which I'm sure Steve will expound on shortly. If you'd like to contact us, if you don't have my direct email from the link that was sent out, you can visit us on our website or on our Facebook page. You can email us on sales@AGM COZA, or if you're an extroverted engineer, you are welcome to call me. The number there will get you to our front desk, and they will direct you through to either me or someone like me. Just by way of introduction, not that he needs it, Professor Bartlett, just his very impressive, and I must say actually highly compressed resume was shared with the invite link. He's currently an associate professor at the University of Utah in the Department of Civil and Environmental Engineering. Must be quite hard to fit that all on your business card, Steve. He is certainly a leading expert in Geofoam. And Steve, we've been talking for several years, and I must say it only dawned on me probably in the latter half of lockdown here last year that perhaps we should be hosting a webinar. So thank you, COVID, for that. Otherwise, I probably never would have thought of a platform like this. And with that, I would like to say good evening to everyone, and good morning to Steve. If you can turn on your video, Steve. I'll release.
Okay, I have my audio on. I think my video's on. Now let me share my screen. I think we'll be ready to go.
Great. Thank you, Steve.
Hope everybody can see that. Well, thank you, Eric, for the introduction, and thank you, Sharon, and for the invitation to speak to you. I am currently in Salt Lake City, but tomorrow morning I'm leaving for Incheon, South Korea. I also serve as the associate chair of our civil and engineering program there, so I go every spring to manage that. And so if you need to get a hold of me in the next while, I'll be in Incheon instead of Utah. But greetings from now from Salt Lake City, and it's a pleasure to be here and talk about a product I think I've been working with in design and construction for about 25 years now. So I've entitled my presentation, Application of Lightweight Fills in Civil and Transportation Engineering. So I'll probably stay mostly talking about those applications, though I have a little bit to say towards the end of this presentation towards architectural and green roofs. I'm going to spend most of this time talking about expanded polystyrene. In the past, I've also talked a little bit about lightweight cellular concrete, which is another emerging technology that we're currently researching. But for now, let's stay with expanded polystyrene. Eric gave an introduction about the lightweight materials. Certainly there, when we talk about expanded polystyrene, we would say it's an ultralight material, particularly in geotechnical applications. So primarily we can think of the weight reduction that we gain with use of this material. It weighs about 1/100th the weight of soil. So that's a distinct advantage when we start looking at applications on soft ground. Also, though you may not realize it, when you look at its compressive strength and to its mass ratio, it still has a fairly high strength to mass ratio because its mass is so low. So that allows us, I think, to use it in civil engineering applications when we protect it in certain manners that I'll show you later in the presentation. So its important functions that we find are certainly settlement reduction on soft ground. So where there's the chance of primary consolidation caused by construction due to mostly embankments and other types of things that are above ground, then we have the chance to use lightweight materials. Also, when we're worried about bearing capacity of roadways and rail systems, certainly it also can be used with some excavation and replacement and used as a lightweight material to improve bearing capacity. I will show you some improvements to foundations and slope stability cases, and then show you also how we can use it to decrease horizontal and vertical loads on buried structures and other things. Certainly what we found in the United States, why we go to this technology is usually to accelerate construction on soft ground. Normal construction, particularly highway construction, which I'm most familiar with, can take several months to complete near a bridge abutment. By the time piles are driven, PV drains are installed, surcharging's added, and the bridge abutments are ready for construction. So if you want to accelerate that to within about a month's time, it's certainly a technology. And I will also use some instances where it certainly not only saves time, but certainly saves money. Okay, just briefly upon the manufacturing process, raw styrene beads are inserted into steam and you go through the first heating of this material. You produce what's called a pre-puff. Then that pre-puff is injected into steel molds and heated again for a second time in the second final heating to produce the somewhat rigid block that you see that are being carried by the workers. I'm going to say just a little bit about design. I think in our conversations after this, we'll have a little bit of chance to talk more in detail, maybe about some design questions. This presentation is not meant to give you all the information about design. It's just mainly focused on applications, and then I will certainly be able to answer any design issues that you may ask me. The primary objective we have in design is not to overstress the EPS from localized loads. And I'll show you the strategies how we do that in a minute. But in terms of design values, we use the compressive resistance at about 1% vertical strain to represent the allowable stress on the EPS. So in the case of EPS 19, that's about 40 to 50 kPa. I don't really quite remember, but we need to keep those stresses with that in that range. So we're staying, if you notice here, well within the elastic range of the material, about by a factor of 2. And so we have found that if we keep the combined design and live loads within this limit, then the EPS doesn't creep with time. If you exceed these limits, particularly in terms of the dead load, then you can open the possibility of excessive creep within the EPS itself due to overloading or overstressing. Okay, rapid construction. Here you see a geofoam placement on the left in Kuala Lumpur, and it truly can be done by individual workers or a crew. Sometimes the blocks are larger than these, and certainly a crew of 4 people can move and place these blocks. So let's just show you some applications quickly. Roadway construction over soft soils and reclaimed land. is one of its primary uses. I'll talk a little bit about bridge abutments and underfill accelerated bridge construction. I have some thoughts about that. Retaining and buried wall backfill, culverts, pipelines, buried structures, rail embankment, and slope stabilization, and landscaping applications. So in essence, this block diagram shows you kind of the general concepts. You place EPS over poorly subgraded materials. There's usually a separation barrier here. We quite often use a non-woven geotextile, sand placed on top of it so that we can get a leveling course for the geofoam block. The blocker then placed. And then it's customary usually for heavy trafficked areas, not maybe for lightly trafficked areas, but heavily trafficked areas, to top the EPS off with a reinforced concrete load distribution slab to distribute loads, and then the pavement sections constructed on top of that. The first use of EPS started in 1972 in Lillestrøm at the Flom Bridge. This was on PD ground, and the problem there was that as the settlement occurred near this bridge approach, the highway maintenance engineers came in and just increased the asphalt thickness to make up the difference. So they kept adding load to these poor soils, and essentially the settlement just continued with time and didn't mitigate. So the idea was to come in maybe and remove some of that, certainly that asphalt and some of the subsurface soils, the embankment, and replace it with the lightweight materials. The Norwegians had been exploring the use of expanded polystyrene for insulated pavements to prevent the melting of permafrost. So they naturally had some experience with it. In this case, they switched from a insulation strategy to a lightweight embankment. Their first concept was to have the EPS blocks tilting inward towards the center line and then make up the difference with some polyurethane foam sprayed in. And they tried that a little bit in a prototype, but that didn't work so well. So they replaced that with just flat lying block capped with a, well, let's see, it was about 4-inch, so about 100 centimeter thick low distribution slab, concrete slab. Okay, fast forward in time, this technology was used in Norway, brought to then Japan. The Japanese did a lot of development in the 1980s using this for many of the similar situations that were used in Norway. And then I found myself in 1996 as part of the I-15 reconstruction team in Salt Lake City. Our job was to reconstruct the main interstate through the city in about 3.5 years, just prior to the 2002 Winter Olympic Games. So I was on the design build team and I was a designer for this project. I also left after this project, joined the university, and did some instrumentation of some of the technologies. So I'm going to spend a little bit of time discussing I-15 to give you kind of the setting of how it was, introduced in a large way in the United States. So here's some of the project details. I-15 runs north and south. The city here, the city center is down in here. The soft ground areas in the northern half of the project. And these show geofoam placement areas. About 100,000 cubic meters of geofoam was placed for this. So it was at the time, and I think it's still close to the largest geofoam project ever done. A little bit of background of why we need maybe some lightweight materials or have problems with settlement in the Salt Lake areas. The Great Salt Lake, as you know it here on the right, is a remnant of Lake Bonneville. Bonneville is a Pleistocene lake that left large lake deposits throughout much of the western part of the state. And some of those deposits are compressible clays. So just in the downtown Salt Lake City area on the left, we're looking at meters. We see some recent alluvium, which is about 7 meters thick. And then we see the Bonneville sequence here, where the cone penetrometer soundings are quite low. The upper Bonneville clay, quite soft, classifies as a CH/MH material. Flat clays to last fat elastic silts. And then the lower Bonneville clay is not as plastic, but still compressible. And then there's some sandy interbeds. The piling for this project went down to these deeper alluvium to approximately 20 to 25 meters deep. So it's these two units, the upper Bonneville clay and the lower Bonneville clay, that cause a lot of primary consolidation settlement. So this is a settlement record from the 1960s. The upper green line that we're looking at shows the fill height. The time scale here is on a semi-log plot. It's logarithmic. So we see 1965, 66, 67, 68. So we see much of the fill coming up to its height. Another stage brought up to just prior to 1965, which was just under 40 feet. We see the subsequent primary consolidation caused by that. This loading event caused about 4.5 feet. So it's at about probably 1.3 meters or so of primary consolidation settlement. Also, very importantly to this project, since time was of the utmost consideration for the Olympics, is to look at this consolidation curve. The time rate of consolidation is approximately 2.5 years, which poses a very now major challenge to a fast-paced project that we were trying to do at that time. So just to give you an idea of the typical construction done for embankments for the I-15 reconstruction project was prefabricated drains down through the Bonneville deposits. Then in some cases, it's a widening project, so we were tying into existing embankment. A geotextile was used to help with prevent some shear failure through that system. Most of the walls were mechanically stabilized earth walls. I'll show you some of those in a minute. And then surcharge was applied on top of this. The purpose of the surcharge was to reduce the secondary compression or long-term settlement of the embankment and pavement system. Of course, to reduce the time for primary consolidation, then we were relying heavily on the prefabricated drain. So this is the typical construction. And the PV drains are being installed. You see surcharging going in place, and in some places, geotextile reinforced slopes going in. Just a typical construction. I also should mention in one area we did some soil improvement. These were lime cement columns, technology introduced to us from Sweden, and we did some soil improvement. Unfortunately, this turned it out to take, it worked quite well as far as the settlement mitigation, but it was the length of time of construction of doing the soil improvement was just not fast enough. So we had to go in some cases to different means. These are just some pictures of the lime cement column installation. Here's a column here with my Olympus 35mm camera cap on it, and you can see the erection now, the MSC wall with the welded wire tiebacks going back in. And then this was raised up to about, this is a large embankment here, about 10 meters high. So there was some geofoam introduced on the project, primarily in areas where there were utilities. So if there were gas lines, sewer lines, sometimes fiber optic, sometimes some high voltage transmission lines, when these got into the area of settlement influence from typical embankment construction, then we had to go to lightweight construction. And what we were able to do is construct these embankments rapidly, causing no settlement, no appreciable settlement. And so we didn't have to relocate utilities. And that was our primary motivation for using EPS. I should show you in this cross section here, you see the EPS block here being placed. And then this area up here represents the reinforced concrete slab. We used a 6-inch slab. And then on top of this, the base, which was about 2 feet thick, and then 14 inches of concrete pavement was our section. So this is heavily trafficked interstate. So we had to go to these countermeasures to protect EPS. I should mention too that these panel walls here that you see were precast tilt-up panel walls, which also allowed rapid construction. And you can see the footing here in this diagram for the tilt-up panel wall. So here is one stretch of EPS embankment. It's 3 city blocks. I think these blocks, each of these reaches of EPS embankment are about 200 meters long. So you see in aggregate about 600 meters of EPS block being placed here. And then again, this was primarily in areas where in the city streets where there were underlying or nearby utilities. Here's just some more construction about the low distribution slab. Below here is the EPS. It's not quite as white because it's kind of been dirtied from construction. But then you see the reinforcing bar epoxy coated, and then the 6-inch slab being poured on top of this. So once this is in place, the contractor can do about what he wants to do in terms of construction. They can drive traffic on this and trucks. On top of this, then would go the base course and then the final pavement section. So after I left the project, I was hired by the University of Utah in about 2000. And so I realized the importance of looking at some of these rapid methodologies that we were using for the project and get their long-term settlement behavior. Our settlement goals was to reduce the secondary compression of the foundation soils underneath the embankments to have no more than 75 millimeters in 10 years, or approximately 3 inches of settlement in 10 years. And so that's what our whole goals were. And so all of our surcharge design and lightweight fill design was meant to meet those goals. Though one thing that was interesting to me at the time too was to understand the compression of the EPS itself as we place the overlying pavement section, and also to understand its long-term creep behavior. So I'm showing you one of the arrays that we put in. There were 2 locations at this array where we put in instrumentation to measure the vertical strain. I won't get into the details of the instrumentation, but this is highly reliable data. So at the end of the construction at both these areas, we see that we achieved about 1% compressive strain. So when I gave my introductory stress strain plot, remember I said that we were trying to keep the, we're using the compressive resistance that corresponds to 1% strain. So our dead loads are right there at that limit. And then we see the subsequent creep strain we've now monitored for 10 years, and it's about an additional 0.3% and about almost 0.5%. Our goal in 50-year strain was to keep it above this limit. And as we project this data out, we could certainly see that the design is working as intended. And the embankments are slowly creeping, but it is of no engineering significance. We did some other arrays for the PV drained areas, the normal embankments and the surcharging strategies. And most of these here are exceeding those goals in 10 years. We have anywhere from maybe as much as 150 millimeter settlement on some of the earthen embankments that were surcharged to some that were just slightly above 75 millimeters. The one lime cement column area I showed you, the soil improvement in terms of settlement performance was very similar to the EPS. The EPS is shown here in blue, and the ground improvement with lime cement columns is shown here with solid triangles. So what did we conclude from this project? Certainly that geofoam fills performed as expected with no major issues. We have not now, after almost 25 years of trafficking on these, have seen no problems, no significant settlement or differential settlement. Approximately 1% vertical strain occurred during construction, primarily again due to the dead loads. There are some strain that was caused by that placement of the dead loads on top of the geofoam. Some of it's due to seating. The block are not perfectly planar. There's a slight arching or curl to them. We were not trimming the block in any manner. So some of this is just seating as we push down a little bit on the block. And then some of it is truly elastic compression, 3.3 to 0.5% in 10 years, turned out to be about 15 millimeters of movement at the surface. We looked at the vertical stress distributions. They seem to be within what we expected from our pressure cells. Okay, let's fast forward. I'm going to skip this. This is another use of cellular concrete. So I gave this presentation in Kansas City just a week ago. And I also spent a little bit of time talking about cellular concrete. But let's go back to EPS. About 12 years ago in the Philippines, we were contacted by a block molder there to maybe assist in introducing this technology. So you see kind of a more construction. This is a very wet soil. These are rice paddies, and you can see the groundwater here is very near the surface. So we sub-excavated out to maybe about 1 meter, and then placed a non-woven geotextile, and then you see the sand placed on top of it, and then a roadway built on top of that, which I'll just show you in a minute. So this was done on 1.3 kilometers is my recollection. We probably spent 2 to 3 months in constructing this roadway. So here's a typical section. What we try to do is we sub-excavate out, remove the soil loads, replace them with EPS, and then the pavement section that we place up on top does not weigh, is equal to or less than the soil that we remove, the weight of the soil. So in essence, we can get a zero net loading and not cause any settlement, even on very soft ground. Of course, with EPS, it is buoyant, so it's really hard to go too much below the water table with this, and even if you were, you would have to do construction dewatering. So generally, we're placing this just at the water table, but construction becomes more complex if you go below the water table. Next topic, bridge abutments and underfills. So quite often, if we're underfilling space underneath the bridge, instead of putting soil loads on that abutment area, we can certainly put in a wedge of EPS underneath it to help in that abutments. And this is strategies used time and time again in the United States. What we gain from that is certainly soil loads, whether we're looking at abutments or culverts. We're placing horizontal loads against that, and can also have problems with settlement and bearing capacity in this area. If we use the EPS, we can essentially fill this up, support the roadway without adding that load. And we can also leave a gap here, a vertical gap, and not put any horizontal loads against this. So that gives us some advantage in certain cases. Also, I should point out, if you use lightweight materials behind the bridge abutments themselves, the idea then is you can prevent, a general shear failure occurring in the abutment area. And I'll show you a case of that occurred in Norway later on, a shear failure like this. So back to I-15 reconstruction, one thing I forgot to mention, if you're using this in bridge abutment areas, then what you do is you pre-strike the piles. You don't drive them to final depth. You drive them to a preliminary depth, and then you build the EPS around the piling. And then when you get ready for final construction, you come and you can drive the piling to their final depths once the load distribution slab's poured. So this is the abutment area, and then you can see a bridge now coming up. This is a pile supported bridge, but the embankments behind it are expanded polystyrene. So, I've done a lot of work for the Utah Department of Transportation. I've worked for them as an engineer, and I've also been a research engineer for them. And this is by far the most common use of EPS that we have in Utah, is this kind of construction. Just some infill here. This was a case of bridge. They wanted some temporary infill, and you can see that this case, the EPS is non-load supporting. So this is just putting in infill without any, it's non-structural infill. Another interesting case was in St. Louis. I was approached several years ago. There's a tunnel that went through the streets of St. Louis, and they wanted to abandon the tunnel, but they didn't want to bring in fill. They wanted to abandon the tunnel and build a roadway on top of what was the tunnel. And they didn't want to fill this in with normal fill, the tunnel area, because of the fragile buildings that were really adjacent to it. So the idea then was to come in and fill in at least all of that tunnel for the most part with expanded polystyrene, and then construct the roadway on top of it. So this is called Tucker Boulevard in St. Louis. It's a well-documented project if you're interested. It won several awards from ASCE. Let's go back to Norway a little bit and talk about accelerated bridge construction. So sometimes you have to go really, really fast, and sometimes you need even temporary bridges. And that was what was needed in Norway near the Swedish border. And the Norwegian Public Roads Administration had a quick clay. For you that are not familiar with quick clays, they are kind of scary, is the best word. If you disturb this clay in any way, it liquefies and can cause all kinds of damage. So you can't drive pile through this. It's hard to even do ground improvement. So in this area, it was underlain by quick clay. So the idea was at this time was to build the abutment areas with expanded polystyrene, put a footings on top, and then put in this case, this is a steel truss bridge, lightweight bridge placed on top of the EPS. So here you see it under construction. The abutments are going in. They're doing the formwork for the concrete foundations. And this is just the finished product. This was supposed to be a temporary bridge, but it worked so well, they left it in service for 17 years. And then I'm told that when they deconstructed the bridge from this area, they uncovered the EPS and they used it again. So I guess it's a case that we can even say this material is reusable. Another case that we learned from Norway was quite interesting. There was a general shear failure underneath this area, again, due to the quick clays. And this was a concrete bridge, pile supported. You can see one of the vents here. And so to remediate this bridge, they had to come in and shore up the bridge with temporary shoring. And then on this whole abutment area, they excavated out and replaced it all with expanded polystyrene. This is EPS 100. This would probably be pretty similar to about what we used on No, this would be more dense. Oh no, I got to back up. I'm not sure. But anyway, this is a less dense EPS and this is a denser EPS as a trapezoid underneath the abutment area. I've worked with two materials that could be used for modular bridge construction. I guess my animation here, let's see if my animation works. Okay, so you have soft soils here. So whether I'm talking about cellular concrete or EPS, it would work for either type of technology, but you would come in and place a concrete slab, place the lightweight materials here, build the approach slabs, bring in a modular bridge. And then if you're in high seismic areas where I find myself in the Western US in high seismic areas, then you need some type of seismic restraint system for this. So this is a very fast way of building bridges. I really believe if somebody thinks about how to do this and pre-plans this, that a temporary bridge could be built in 2 to 3 weeks, no problem. Okay, retaining walls. This is similar to using EPS in backfill behind bridges. Now we're just doing it behind retaining walls. So there's nothing really new here, really, in terms of engineering. Though this is a retaining wall, I do want to introduce the concept of lightweight fills against buried structures. This particular case down here at the bottom, I want to talk about. This is a parking garage, and the reinforced concrete design of the walls here for the parking garage were designed to not have any significant lateral load. So what they did in the first construction of this area was they put a mechanically stabilized earth wall, made it vertical, and they didn't have this concrete wall touch the mechanically stabilized earth wall. Unfortunately, for the backfill for the mechanically stabilized earth wall, they used a compacted clay sand. They compacted dry of optimum. It looked really great during the summer and fall, but when this area got wet during the winter, that wall moved and deformed. It settled 6 to 8 inches, but more importantly, it moved horizontally and began to touch the wall here, the concrete wall, which was not designed for those lateral loads. So kind of in an emergency situation, all of the flat works around this building were removed. The wall was excavated down to about half of its height, and the expanded polystyrene was brought in and replaced so that they could redo the retrofit of this and bring this back up to this elevation here. So a use of lightweight fill to stop a very serious problem. And all of the hotel, this is a hotel, had to stay in operation while all this reconstruction was going on. For new construction, course, placing lightweight fills around. This is the federal courthouse in Salt Lake City. This is a hospital, and you see the lightweight materials. This is to reduce lateral earth pressures and also seismic lateral earth pressures around some of these buildings. The courthouse is very interesting in that the courthouse itself rests on a mat foundation on top of the Lake Bonneville clays, so it doesn't have deep foundations. And then the lightweight materials were used to not increase the loads on the mat. Then they wanted a significant berm around this building. Frankly, this berm is for blast protection. In the US, we had a very severe case where a moving truck with explosives was parked as a terrorist act outside the federal courthouse in Oklahoma, and exploded and collapsed part of the building. So this is a berm now. It's mostly expanded polystyrene as a blast attenuation. Culverts, pipelines, and buried structures also can be prone to settlement when we do widenings or roadway embankments around them. So similar ideas, lightweight materials usually placed in a trapezoidal configuration. We want this interior slope here stable because we're not using the EPS for retainage here. We're just using it for lightweight infill, and then whatever protection you need on top of it for whatever system. So give you some ideas here. I'm going to go to the right first. This is a highway construction of a arch culvert. And you can see the EPS is being used here. It'll be placed here. It's being used again as lightweight fill to protect settlement damage to this culvert. One that I'm going to show you a little bit more detail about is back in the Salt Lake Valley. This is a culvert. We're having, this is Union Pacific Railroad line up here. And this is a widening area. They wanted to add 2 tracks for our commuter rail system. And this is in a settlement prone area also. So the expanded polystyrene is being used here. And I'll talk a little more about this in just a minute. For pipelines, it's pretty obvious. If you put new fills on top of buried pipelines, then you have a chance of causing bending and eventually rupture of the pipeline, depending on its nature, which can be very problematic. So new fill can be used with constructed with extended polystyrene. One interesting case of this, kind of a nuance that we've never really thought about too much, is we have earthquake faults that are on the eastern border of the Salt Lake Valley, and I'm showing you a normal fault here that you can see in the shadow area, which is what we call the Wasatch Fault. This fault is capable of probably 2 to 3 meters of vertical offset during any one event. And we have, in the case of this project that I'm going to show about, the potential of high pressure gas lines being ruptured as they cross the fault. Here's some ideas of what faults look like. This is one in Montana. I'm not sure where this is, but you can see the damage it would cause to a pipeline. Of course, if you have high pressure gas lines and rupture of these gas lines during an earthquake due to faulting, then you have the potential for a conflagration, which could be very damaging. So in Alaska, they thought about putting the pipeline, this is the Alaska pipeline, putting on runners. This is to prevent against strike slip falling where the primary movement's horizontal, like this. So you can just have the pipeline shift back and forth on these runners. If you cross normal faults now where the movement is vertical, then they thought they would just bear it very shallowly. They've propped up the pipe and they're putting some backfill on it, but the idea is to keep the amount of cover on the pipe to a minimum. So we took that idea, this latter idea, because we're in Salt Lake Valley thinking a lot about normal faults and high pressure gas lines crossing them. So we thought, well, instead of using sand for the lightweight backfill, we would use expanded polystyrene. The sand is used around the pipe. This, in our case, was high pressure steel or high tensile steel, and it had to have sand for cathodic protection. And so there's some sand placed around, and then the rest of this backfills with expanded polystyrene, a small concrete slab, and then asphalt, because what we were doing is we're going to place this across roadways because the faulting was occurring right through the roadway also. So we did some modeling of this concept. The idea is on the downdrop side of the fault, where the fault goes downward, the pipe's going to want to move upward relatively. through the soil cover. So we just thought we'd put for lack of better words, an EPS cork in this trench. So as the pipe tries to move up, it just pushes that cork upwards and pops up. And the news is yes, we told the highway department we're going to do some damage to their highway. But the good news is that pipe would not be ruptured. So we showed the concept to the gas company in numerical modeling. We did some full scale tests, which I won't belabor too much, but this is the uplift behavior of a pipeline being uplifted through a soil cover. In our full scale tests, we're reaching maximum forces of about 525 kilonewtons on a 1 foot diameter pipe. This is the behavior with the EPS system. So not only markedly changed the peak, but we've taken that peak and put it out here at a much greater displacement. The pipeline engineers were elated with this concept. And so this is the normal procedure of fault crossings, normal fault crossings, at least in the Western US. So you see the construction here, the high steel tensile pipe. This has a lot of ductility. So it's a robust pipe. It's placed down, and then there would be the bedding sand. Here's the EPS cork. In this case, we decided to put geomembrane on top to protect for any petroleum spills so that we wouldn't damage the EPS. Then we see the rest of the construction going on. Eventually, this will be brought up to grade, and this is right down through the middle of the roadway. Rail embankments, my time's short, so I'll get through this quickly. Yes, we have supported rail embankments on EPS. We have two systems in Salt Lake City. We have our light rail system. We have our commuter rail system. And these commuter rail engines are diesel locomotives, approximately about 80% of the weight of a heavy freight locomotive in the United States. Our light rail system, we had crossing not only through the I-15 corridor, which is all of these yellow lines, the spaghetti interchange as we call it, but also had to cross the rail lines, Union Pacific Rail. And so we use lightweight fills across the rail yard. This is an approach embankment. This is an intermediate embankment. So there's one bridge here. There's another large curved steel bridge going to be constructed here. You see the EPS up to about 13 meters here. You see the precast panel walls coming in. Some other details of this construction. Then the load distribution slab is being poured. It's being poured in steps. We found it easier to pour these slabs horizontal and then fill this in with some concrete than to try to pour this as a continuously sloping low distribution slab. Then the catenary poles are coming up for the light rail system and being poured. That foundation's being integrated into the low distribution slab. So that's the light rail system. And then you got to have to imagine this with earthen and baked, a little bit of topsoil on top of this, about 2 feet for landscaping. For the heavy rail system, you can see the EPS being used. Here's the culvert that I showed previously. Well, here it is here. And the widenings be affected in this area. So we see a trapezoidal shape being used. They initially wanted to put a geomembrane on this for petroleum spill, but unfortunately, the slope's steep enough that under seismic loading, this geomembrane on top of plastic EPS is not a good idea. It doesn't have enough frictional resistance. So they removed this geomembrane and then just left it in this configuration. And now you see the final configuration with the train and the landscaping on top of it. So this is the EPS embankment. This is the adjacent earthen embankment. Here's the culvert. And we did some monitoring. I won't get into the details, the whole dissertation on this, but what we did is we monitored the deflections. Let's see if I have those slides. I don't, so I'll have to report what we saw. When we monitor this from the deflection of the rail system that we constructed here, I think we saw about 4 to 6 millimeters of deflection. On the earth embankment, it was 10 to 12. So we actually, because of the low distribution slab, I think made this system even stiffer than the earthen embankment system. So that's good news for rail performance. And this has been in place for about 10 years. Slope stabilization, we'll go really quickly. You have side slopes that could fail if you put earthen embankments on them, so you use lightweight embankment. This is a project in northern Arizona. So we can see some construction in my sketches of what's happening here. This back slope is being stabilized with soil nailing and shotcreting. Then the EPS embankment is going to come up again in a trapezoidal shape to form the road widening. And you see the foundation for the precast concrete pad, the footing. So you bring these, you bring this shape of EPS up. You can see now they're still being used for their slab on top, the low distribution slab. And here's just another shot of it. So you're stepping up through this area, and then here's the final product. Okay, just quick, I want to say a little bit about landscaping. I was involved in Geo Shanghai with Disney. The combination of US and Chinese engineers had determined from preloading, they were using a vacuum-induced preloading strategy, that they got about 4 meters of pre-consolidation stresses, meaning about anything below 4 meters could be constructed with earthen embankments, but anything above 4 meters height needed lightweight embankments. So certainly when you get into some of these elevated plazas and landscaping areas, they were above 4 meter height, above the original ground. And so you see the sculpting of the EPS and creating terrain for the Disney project. Another one that I've just finished was the Lucas Museum in UCLA in Los Angeles, University of California, Los Angeles. This is George Lucas of Star Wars fame. He wanted a museum that had quite a aerodynamic shape to it, spaceship-like shape to it. And now you see the EPS being used on the green roof. The real challenging part of this project is because of the design earthquake, is how to design this and also have the landscaping survive the design earthquake. It's the most complex green roof I think that's ever been attempted. And it's currently under construction. There's several awards. Some of these projects have won. I think the most important, I think the most prestigious is the Opal Award, as we call it, the Outstanding Civil Engineering Achievement Award. So this is a single award given to one project yearly by ASCE, and in 2002 for the design build team for the I-15 reconstruction for the Olympics. The team that I was on won that award. Okay, I think I'm done. I'm slightly over time, so I'm told I should pause now, and I think we have some questioning. Is that what's going on?
Yes, thank you, Prof. Bartlett. If I can just reintroduce Eric to come back.
Yes, I'm still here.
Thanks, Eric.
No, great. Steve, that was fantastic. And I definitely sold you short on my intro to you. You're much more than just the associate chair for the University of Utah. I mean, the quantity and quality of projects that you've been involved in is amazing. I think people will post their questions on the Q&A group.
Okay. Okay.
And we can go from there. Otherwise, I wouldn't mind if you also could discuss maybe a little bit on, maybe do the Q&A first, and then maybe a bit of a discussion on the project that we're working on in Clarewood.
Sure, I can do that. Let's get through the questions. Are any barriers provided in layers to prevent accidental solvent spills from reaching the EPS, acetone, gasoline, petrol, etc.? So in the United States, the Federal Highways Administration has adopted 2 general strategies for this. One, if you want to protect this, I think the least expensive would be a geomembrane. So a petroleum resistant geomembrane can be placed atop the EPS to protect from gasoline and petroleum spill. On the I-15 project, we were certainly designing a more robust system. And for our case, the accidental spill would be protected by the low distribution slab. So what would happen, because the interstate also has its storm drain runoff system, is any petrol spill on the urban interstate would be captured by that storm drain system, but the EPS would be protected by the concrete and then certainly the tilt-up panels. To date, we don't know of any petroleum damage to any of these systems that I'm aware of, at least certainly in the United States. I can't speak for Europe and Japan, but we've never damaged any of these. But we do have, I think, appropriate countermeasures that we can take in design and construction.
Besides that, Steve, I mean, on the Clearwood project, this is also something that came up.
Right.
I believe that, you know, if you did have a rupture of the pipeline, you know, a subgrade leak, that there would be remedial work to do there anyway to attend to the leak in the pipeline. So you would be needing to dig out the geofoam to attend to that and then remediate afterwards.
Well, you bring up an interesting point that I forgot about. So you jog my memory. So rewind about 1998, and it's the same argument we used, that even if you had normal soil or EPS, regardless, if you had enough that it really damaged the roadway, subsidence and some localized settlement or subsidence due to dissolutioning of the EPS or damage of it, whether that's EPS or soil, you're going to have to repair it. And the soil would be petroleum contaminated soil in the US, that would have to be treated as a hazardous waste, where the EPS is not considered a hazardous waste. It is a petroleum project, so it could be incinerated. But my point is really whether, I can tell you truthfully that an EPS fill, if it were slightly damaged, and it still has not happened, and I think our countermeasures have been very good, is that it would be quicker and easier to repair an EPS fill than an earthen fill. I think I can state that pretty emphatically. Terms of fire resistance. Okay, the Norwegians had an instance where they had a EPS product that had no fire inhibitor in it. And so the EPS block without a fire inhibitor, at least when you have it to open oxygen, to open atmosphere, is combustible. In the United States, we use a fire inhibitor so that EPS will not burn unless you introduce a continuous oxygen source to it. And so we think that has been solved. During the I-15 construction, let me just say one quick anecdote. During the I-15 construction, we had a crane fire that happened over the EPS section when it was in its final configuration, meaning it had all of its protective layers on it. The crane touched a high voltage line. Luckily, the operator got out without being electrocuted, and that crane burned for about 45 minutes before the fire department put out that fire. The heat was intense. Also from the high voltage line was running for about 20 minutes before they shut it off. And we had no damage to the EPS at all, right on the EPS section. So I think we have a very good case history that shows the protective countermeasures we used would protect against fire. And we are using a fire inhibitor in our block, at least in the United States.
Yeah, no, that's true, Steve. So I mean, even here we also we use fire retardant grade materials.
More than one question. How do you think the design of the how do you look at the design of the pavement transfer slab? Okay, we've had some discussion about whether it's needed or not in some cases. For heavily trafficked interstate truckloads in the United States, my advice is you need it all the time. For lighter traffic roadways and that, you can omit the low distribution slab, but you have to bury it deeper. And you have to probably use a higher density to protect it from localized stresses due to the tires. How I design it personally is those systems become very complex. They're multi-layered, and I use finite element methods to check what I think the induced loadings are. And I'm using currently a three-dimensional finite element mold because I'm looking at a low distribution slab, untreated base, pavements, I mean a low distribution slab, and then EPS. So you can't really do these from simple calculations. So I've done several of those calculations over the years to try to qualify the EPS and pavement design to make sure that it won't overstress the EPS. Okay, how do you present hydrostatic pressures from developing within the mass? Well, there's some different thoughts. This couldn't also be a question that we have to consider about different design scenarios. Let's just talk about flooding most of the time, what we do then for flooding is to place EPS. Of course, we're placing this above groundwater usually, or almost always. And so once the EPS is placed and we in its final roadway configuration, we have enough weight on top of it that we would not have any hydrostatic uplift due to flooding. Groundwater, I've never placed EPS below groundwater. And so if you have a large groundwater rise for some reason, that could be problematic. My advice is if you have groundwater issues with it, where you're looking at substantial groundwater rise for some design groundwater event, then I would recommend to you permeable cellular in the groundwater zone. You still have to do water and place permeable cellular, but it's not going to be as buoyant as EPS. But placing EPS below groundwater is problematic from the construction and from the design perspective. Let's see, how do you prevent slide cracks between new and old fill? You can take your low distribution slab out into that transition zone and prevent that if you're tying into new fill. So you taper the EPS and the trapezoid. I hope you can still see me. Go up this way, and then you put a low distribution slab that goes out into the new area, the old area fill, and you can prevent any differential cracking that might occur. On the side slopes, we're benching those into the side slopes. So we haven't seen that occur into the side slopes, and then we're covering that. So whether we're doing it longitudinally or transversely, I think the key is what you do with your low distribution slab on top and how much you step it out. What is a typical slope angle to prevent superficial sliding on the layer? EPS has a sliding coefficient of sliding about 0.6, so that's about 32, 34 degrees. But you notice we don't really put layers that are inclined. We use terracing and construction of kind of stepping embankments rather than that. And that helps that situation quite a lot. Okay, as to how you not only configure embankment, but it does have some internal friction. If you do need to have some additional sliding resistance, particularly I'm going to do a lot of seismic design, I could give you a whole presentation on that, but there are countermeasures. And that was one of the big challenges for the Lucas Museum, was keeping the EPS from sliding under the design earthquake event. But I don't want to get into all that, but there can be some measures, but generally they're not needed. If your slopes are, probably less than 25 degrees and you're sloping and terracing, and on where you have seismic considerations, we believe that most of these systems are pretty stable under 0.6 G peak ground acceleration or less. But that's a long conversation. How do you tie up the tilt up panels? They're tied with the low distribution slab, and you need a somewhat flexible connection because you know that the EPS, when you load it, it's going to move downward a little bit, so you can't make a rigid connection, but we tie it to the low distribution slab. Have you ever encountered scenarios where you come across water during installation? Okay, here's what happened in the Philippines, and it was to another phase of construction, not the phase I showed you. They were placing EPS block and constructing the roadway I told you, and they were not in their final configuration. They did not have the final roadway in place, and they had a typhoon. And it came in, obviously, EPS without the overburden of the road base and pavement on top of it had a factor safety of less than 1 against buoyancy, and it moved. So what I would tell you is, if you're worried about storm events or other things that could cause flooding and you're crossing lowland areas, and I'm still talking mainly about construction above groundwater, is that you sequence your construction not to leave your EPS in a temporary configuration for long lengths of time. In other words, don't be too sequential about this. As you come across with the EPS, you need to be following across with the whatever you're placing on top of it. So you keep that part of the EPS that's still susceptible to flooding and buoyancy at a minimum. I think that's the smartest strategy. I may have missed the technical part. How elastic is EPS? How sensitive it is to cyclic loading? Example between an integral bridge abutment. Okay. How elastic is EPS? The elastic range is approximately at 2% compressive strain, and the modulus associated with that EPS is according to the density. So you can get from the manufacturers the various vertical strains at 1, 2, 5, and 10%, and you can determine that in the 1% range, where we're limiting it to 1% vertical strain. I think EPS behaves relatively elastically. Beyond that 1% strain range, you're starting to introduce some plasticity. How does it behave in cyclic loading? Great. We've done a lot of cyclic loading, triaxial cyclic loading on EPS. And what we were doing was taking it to 1% vertical deformation under a dead load in the triaxial system, and then cycling it higher to that. And I have cycled it an additional quarter, half, and 1% vertical strain beyond that, and I can show you the data. But certainly, as you get above that combined 1% strain of vertical and cyclic loads in the EPS, and you get above that, you're going to expose yourself to additional creep. And I have some ideas of how much that might be. But I would caution you, at least for roadway systems, of not ever exceeding that 1% allowable stress. And that's from the combination of dead load and live load and any cyclic load you have. EPS behind an integral bridge abutment. I don't know what you're trying to accomplish. If you're trying to use it as some type of soft material for thermal expansion, we put EPS behind integral abutments. But the problem, if you put EPS in the abutment area itself, and again, I'm mainly thinking about seismic conditions, the abutment itself has to take up all of the seismic thrust. So that means that abutment has to be designed for all horizontal loads in what we call an abutment. Integral abutments, we certainly use it as lightweight fill to approach integral abutments, and our integral abutments are pile supported. I'm not sure I answered that very well. Maybe we can have a follow-up question on that. Any other questions?
Steve, it's Garth James here. You missed Ross Dole's question at the start there at the top.
Oh, okay. Would a retaining wall with EPS behind it need to be designed for any passive earth pressure or close to it? I've seen it done both ways. So what we were doing on the I-15 project is that vertical face on the outboard side, the outside of the embankment, was designed vertically. And the tilt-up panel wall, which was setting in a slot foundation system and then tied to the load distribution slab, had a gap between it. So we were not really designing that for any earth pressure wall or any earth pressures at all. I've seen other cases where the EPS is touching the wall, and I've designed it that way too. What's great about EPS is it doesn't have a very high Poisson's ratio. It's about 0.1 Poisson's ratio. And so what you find is, even though you may be putting vertical load on it, your horizontal load is greatly reduced. And we can anticipate what that might be. I have to do this through computer analysis again, but we can anticipate what that loading might be if you do design some transfer of earth pressures to the wall system. I think if you think about this wisely and do it right, at worst, the highest earth pressure coefficient you would have to design for now, probably switching to a more rigid wall system, is the active earth pressure case. And if you put EPS in your active wedge, you have not a lot of mass. And if your back slope behind that wedge is stable, you still don't get a lot of transfer load. It's a complex question you asked, actually, and it really depends on the system, the configurations, but all of these we've done over the years, whether we've tried to leave a gap and have no earth pressure against the wall system, as you saw in the retrofit in New Mexico, where I showed the MSC wall being excavated out, that EPS was being benched back and designed so it would not put any further earth pressure against that wall system. But in new construction, I've seen places where we have butted it against the wall, and the wall geofoam backfill earth pressure thing becomes a little more complex. But there are some design strategies depending on what you want to do. But the key, if you use a lightweight wedge, no matter what you're using, you don't have a lot of mass. So in a way, earth pressures are not as big as you think, particularly if you have a trapezoidal configuration of EPS against the wall system. Okay.
Steve, it's Garth James here again. I just, where the question was raised by Frans van der Merwe regarding the widening, where you've got the potential for cracks between the old and the new embankment. Now, traditionally, you have geogrids are used to help smooth off the differential settlements. So in the case of something like what you were talking about on the widening with EPS, would high strength grids help rather than the load distribution slab?
Possibly. We were using it in that transition zone for our capping layer, also for a petroleum spill. And then we did use a geomembrane a little bit on the inboard side to help with that. But it really depends on what, you know, I'm going back to I-15 and you see the existing embankment slope, and we're stepping back into this existing embankment with the EPS block. And then on top of this, the load distribution slab might only extend another 2 meters maximum into that zone. So it just becomes a construction cost issue, really. Both would work as you described. In this case, we were going rapidly and add a little bit of a geogrid. I don't think it helped these systems. We've never seen in any of this system, because we've not induced any significant settlement here. So there would be no really reasons for differential cracking.
Yeah.
So with the lightweight materials, remember this embankment's already settled. This has been here for 30 years. So I think if you're doing a case where you're transitioning from one soft ground technology to another soft ground technology, and there's differential settlement due to both of these, then I think, you know, your idea, you know, has merit. Okay. I just not done it.
Okay. Thank you.
I see France has one more question.
Perhaps a question. What would the cost?
That's for you, Eric. It's about a cost.
Maybe let me handle that first, Eric. You got to be careful with this because cost is always an issue. Plastic is more expensive than earth. We can say that. Let me give you a systems approach, because I think I have to go back to another presentation to find this one. Bear with me just for a moment. The important thing is you have to look at what you're doing and the total cost, not just the cost of expanded polystyrene, because it will not win that competition anytime soon. But you have to look at the system you're replacing it with. There it is. Okay, so we did this. So this is dollar figures are not going to be right on this because this is now 25 years ago. Let me bear with me as I can get this even bigger. So this is cost and schedule. So we took a typical 100 meters of embankment and we used the contractor's cost of doing these. So the line cement column array total cost was about $160,000 for that 100 meters of embankment. This is for 100 meters of embankment. The geofoam was less than soil improvement. Certainly it was coming in at 120 $100,000. And the typical two-stage wall with PV drains, surcharging, two-stage mechanically stabilized earth walls was about 100,000. So relatively, I would say the EPS, if you're just using it for lightweight embankments, is about 20% more than the two-stage wall system with PV drains that we were building. But it's certainly less than ground improvement. Now, here's the kicker. If you are if you're putting in settlement damaging in technologies, which this is, because this will now produce 1 to 1.5 meters of consolidation settlement, and this does not, and you're near utilities, this geofoam becomes the lightweight alternative, hands down. Okay. So you have to look at what are you replacing it with, what systems are you replacing it with, and what are your settlement risks in terms of utility or adjacent facility damage.
Sorry, Prof, can you just share your presentation?
Oh, sorry.
No problem.
I thought I had my screen shared. Sorry. Let me show you the data again then. Can you see it now?
There we go. Sorry, Steve,
Okay.
we let you down there.
Sorry. I had a great story to tell. Now you can see the numbers. So this is the lime cement column treated area that I showed you for 100-meter reach of embankment for the ground improvements and wall construction, about $160,000. These are contract costs. These are not, these don't have profit or anything. These are just raw contractual costs. The geofoam, 120,000, and then the two-stage MSC wall PV drains, surcharging about 100,000. So this is your baseline technology. And basically 95% of the project was created with this lower technology, but it has its schedule impacts. And of course, if there's utilities, then it has all kinds of problems due to the consolidation settlement. So the geofoam came in at about 20% higher, the ground improvement about 60% higher than that. Now let's look at construction schedule. Now remember, time is everything in sometimes rapid construction. So here's your conventional construction in terms of weeks total, 32 weeks of construction time, geofoam 5 to 6 weeks. But the also important thing is in the areas where it was used, it was to prevent the necessity of relocating utilities. So we were doing the construction by or over those existing utilities without relocation. So we save not only time, but we save considerable money in doing that. Okay. So in the case where there's a utility relocation required, then EPS clearly becomes a low cost alternative. Okay.
Great, thanks, Steve. And I think on that, maybe to discuss a little bit about the work that we're busy with in Clarewood.
I think I have that too. Let's see. I cannot give you a lot of project details and design, Eric, because I haven't had the release from the project to do so.
Yes, and I don't think that is what we want to do here, but just to
okay,
discuss.
so I'll just give you general things. And since I did this 3 years ago, you may have to fill in some of the gaps for me, Eric. But at Clarewood, we had a petroleum pipeline that was running parallel to the road for parts of it. And there was the need to reconstruct some of the roadway across the footprint of where the pipeline. Sometimes the pipeline was just adjacent to the road nearby, and in a few reaches of the pipeline, it actually traversed right under the roadway. So again, being a soft ground site, the problem with normal earthen embankments, and that is you could cause some settlement damage to the pipeline itself and ruptures the existing pipeline and in service. So the idea was to construct a lightweight fill, if you will, and then a roadway section on top of that to keep the loads to the pipeline so that it would not cause any settlement damage to the pipeline. And so it was a fairly low-lying embankment, frankly, that was needed of EPS in most of this area, and then a roadway section. I think the real challenge to this project from an analytical standpoint was looking at several cross sections where the thicknesses of cover were varying which meant we had to vary the thickness of geofoam over the project and then do calculations to show the client that the induced stresses to the pipeline were certainly minimal, if not negligible. And that's what I can say from a design standpoint. It was an interesting project. Again, it was just low line embankment and roadway over top of utilities and in soft ground cases. It did take a lot of settlement calculations and a lot of stress distributions to show that we would not do damage to the pipeline. Do you want to say anything else, Eric?
Look, we're actually coming up. Zandile, who asked a question, actually now in the Q&A. She is working with us at the moment, and we are about to deliver our first load of Geofoam.
Oh, great. It's good news.
Yeah, so it's taken a bit of time to get there, but we are pretty much at implementation phase now.
So I forgot to mention that years to do these calculations. So I don't want to leave you with the impression that I did a bulk of this design. I was mainly a senior advisor to the team, and we were discussing, and then Archon went ahead and completed most of the calculations. I handled the 2- and 3-dimensional stress calculations on the pipe itself, but that's kind of what I did. But most of the settlement calculations and the final typicals were developed by Archon.
Yes, I actually wanted to see if Gabby was on the call at the moment.
Maybe so.
I don't think she is at the moment. Yeah. Anyway, she
helped a lot. She helped a lot. She shouldered the burden of most of the design calculations and the certification of the design, the stamping of the design.
Yeah, fantastic. Is there any other questions from the participants?
I see there's nothing in the chat box or in the Q&A. Can maybe we just confirm with the rest of the panelists if there are any questions or final comments, and if not, then we can head into the closeout.
Fantastic.
Let me just add, if there are any follow-up questions somebody wants to do through email, my email address is Bartlett, BARTLETT @civil.utah.edu. Fire me some questions.
Great.
I've been answering for about 20 years now, so I think I can.
Yeah, you certainly didn't turn me down when I emailed you.
I do want to leave everybody with the impression that in its place, when it's used properly, this is a very powerful technology, but again, it has to have project reasons for its use. Okay.
Exactly.
Nothing more from my side, Sharon, but just to thank Steve for a wonderful presentation. It's great that we could put it together, and at least we've got to quite a few people now. We've spread the news a little bit more, and the versatility of the applications as well. Obviously, there's a lot of consideration given to where it is most appropriate.
Sure.
Thank you, Garth, and thank you to Prof. Bartlett and to Eric and the rest of the team from Moulders. Yeah, I definitely am proud to have this new technology communicated to our local industry via SAICE Durban. So it's it's quite interesting that this is so well recognized and well used on so many prolific projects all over the world, and yet we're just hearing about it. And yeah, I'd be interested to hear from Prof. Bartlett what, in his experience, is the biggest barriers to entry to the use of the product. Maybe Eric and Garth can touch on what they believe is the biggest barriers in South Africa, but yeah, in the world, what would be the barriers?
looks like Libero joined us. Well, Jordan Libero. Anyway, I'm going to answer his question because I think it's a good one. Is there a worldwide Geofoam conference this year? We have not one planned, but I think we're overdue. I think the last one we had is 2018. And we did have in the US a lightweight fill conference, which is a virtual conference. So I think it's, I think it's well meaning that we should have a conference again and have everybody, the Norwegians, the Scandinavians, the Japanese, and the US contingencies, talk about their various case histories. I think.
Steve, can you just unshare your screen so we can see you now?
Oh, let's see. Let me do that. I find here, pause share.
Or just you just stop the presentation, I think.
Let's see. Did that do
There
it?
we go. Yeah,
Okay.
because we really enjoy your psychedelic headphones.
Anyway, my feeling is you need some fairly sophisticated infrastructure. And so when I visited India, certainly China, I've been to the Philippines, been to Mexico, and it really depends on what's trying to be done. But the combination of fairly sophisticated infrastructure that demands rapid construction, and particularly in urban areas, I think this becomes a very important technology and a strategy. As you get into developing countries, I'll kind of put Philippines somewhere in that range, but the thing is for local roadways and non-urban areas, you have to ask the question where you might have more time, and other things available to you. This may not be a competitive technology, but when we talk, see, I was talking about urban infrastructure and projects that needed things to be done fairly rapidly, and there's a lot of interferences, and so this becomes an important, I guess, tool that a geotechnical engineer may have. But for rural areas, I think that's less of the case.
That's so interesting. We don't have first world problems.
Well, I mean, I've seen it used in other places where there's not first world problems, where primarily accelerated construction was desired. Okay, so
yeah,
it just really depends. But we had in our lightweight fill conference that we had in October in the United States, we had Silas Nichols, who's the chief geotechnical engineer from the Federal Highways Administration. I think he highlighted two key things that usually bring this, as where geofoam is used as a geotechnical tool. One certainly is soft ground, predominantly settlement issues, and then also accelerated construction.
okay.
That's where it's competitive.
Thank you very much, Prof. I'm gonna just go around. Garth, is it okay to close the session?
Absolutely. I've really enjoyed this, and it's wonderful to finally meet Steve. We'll be in touch, obviously, in the future.
Yeah, I would love to visit you in South Africa.
Eric?
Yes, I'm good. Once again, thank you to you, Sharon, for hosting, and to Steve. Safe travels on your way now to Korea.
Thank you.
Yeah, and thank you
Eric.
everyone for attending.
Okay, thank you so much. I'm not sure if Claire and Sean want to contribute. If not, it's okay. We can just move on to the next part.
Yeah, I think we can close from there.
Perfect. I'm going to say one last thank you to Prof. Bartlett, all the way from Utah in the USA, to open up our events for the year. Thank you, Prof.
Thank you very much.
We'll let you go now. We don't even know if you managed to have some coffee this morning. But
Not
yeah, sorry about that. Wishing you
That's okay.
wonderful travels, and I hope you can join us again on a follow-up. Yeah.
I will. I'd love to. Cheers.
Sharon, if anyone wants a copy of the recording, will that come out on a link?
1 second, I was just trying to share my screen. Yes, thank you very much for that, Eric. We will certainly share the recording of this event and the presentation. It usually comes out about a week after our actual event. So yeah, I'm happy to have that distributed to you guys at Moulders as well, and then you can forward it on. But it will certainly go to our members here in Durban. Okay, with that, guys, I think we've come to the end of our first event for the year. I'd like to say thank you to Moulders and to specifically Eric and Garth for helping put this together. I would also like, Kavita, if you could please put up the details for the Tom McEwen course, the geometrics course in our chat box, and for the LIC 5 and LIC 7 training. Guys, I urge you again, if you can support these courses, that will be excellent. Specifically, or more urgently, the Tom McEwen course, because that is in the week after next. And yeah, I've only heard good things about the course, so I can attest to it being an excellent investment. With that, I want to just say one last thank you to Moulders for not just partnering with us, but for bringing us the groundbreaking knowledge of the incredible Prof. Bartlett. And we're looking forward to doing more things like this in 2022. We will confirm our next branch meeting via email. And to claim your CPD points, it's a very simple, like the method that we used last year. Just please forward Kavita an email on durban@saice.org.za, and she will just do a double check to make sure you've been in attendance at the event for the entire duration. And then we will send you a CPD certificate in the next 2 to 3 weeks. So yeah, with that, guys, I'd like to wish you a good evening, and until the next time, have a wonderful, wonderful week ahead. Good night.
Thanks, Sharon. Good night.